Welcome, everybody, to Stay Curious. I'm your host, Mark Marquette, looking over this wonderful book by our friend Mikey Haddad right here with us, Space Lab Payloads. And welcome to Stay Curious, everybody. Mikey, how are you?
Good, real good, Mark. Good to be back. It's been a while.
Yeah, it's been a while. I know some of you regulars have seen many programs that Mikey's done. He is a mechanical engineer for NASA for how many years?
32 years at Kennedy Space Center.
Yes,
Yeah.
and he is what they call level four guy. And I thought that level three was below him and level five was above him, but no. What does that mean, level four guy
it's
at the
it's
SSPF Space Shuttle Processing
well,
Facility?
that and the operations and checkout building. It's basically the beginning of a whole process of how you put scientific experiments together. That's kind of where it started, was in level 4. Yep.
And it's like an assembly line,
Yep.
okay, in a way. Where level four, I think, is the coolest place to be because they deal with the payloads in the payload bay of the shuttle.
Yes, sir.
Things like showing Joe Tanner, where his tools are going to be, right?
All
When
kind
he
of fun
does a
stuff. Yep. Yeah, we work directly with the astronauts because they're basically working on the hardware in orbit that we're working on ground before the launch,
And
getting
that's
it
what we're going
ready.
to talk about today is what's your fancy words for today's program?
It's a on orbit constraints test. Basically, it's how we were able to connect elements together in space station successfully that were launched years apart. And it's more than just a mechanical. It's kind of more of the all the interfaces that go between those two elements, just not the mechanical interface. So
And
yeah,
here
it's
we got
interesting.
node one and lab one here in our
Yep.
backdrop there connected. And that is really the cool thing about our International Space Station now orbiting for some 26 and a half years, 25 of them occupied, is the pieces were never put together on Earth,
Nope.
were they?
No, sir.
Nothing was ever put together on Earth and then assembled and then taken up. Am I correct?
Yes, sir. That's it. And how do you make sure all that's going to work? That's what we're going to talk about today.
Now
Is
we
a
had
small piece of that.
Russia, this is
Yep.
international. So
Yes.
you had metric, you had imperial measurements that we use in
Had the
America,
Europeans, the Japanese. Yep.
and
Okay.
and
Yep.
and and everything pretty much worked, didn't it?
Yeah, well, to a point.
We're going
Everything
to talk about some of
we're
those that
talking
didn't
about
work here.
some of the things that didn't work out too good. We actually fixed before launch, which is
So
why
that's
kind of
what
why
you're
we're
going to
here.
learn today here. Marty Winkle is our on the board here today. We had a little, we never know, perfect shows for months, and then Marty can't get it up and running today like usual, but that's okay. He called Trekkie Techie, and she took care of it for us there. So if there's a little hiccup here, let us know. My hair's blowing in the wind because we're 80 degrees inside here. Our air conditioning unit broke down on the main, and we're looking for the part to come in and get the repair, and it's $5,000, and such is the plight of nonprofits, and we're gonna manage that as most places do. We're gonna pay it and then find out how to cover that cost out of some money we'll probably borrow out of. But this is who's parked on the space station right now. Well, let me go back there. I'm going the wrong way. I'm going the wrong way and blowing the uh, a little bit of, since we're going to talk about the space station, let's see who's parked on the space station. I go full and yeah, there we go. I see what to do, Marty. I went full and then I had to hit image. We've winnowed down, I think Cygnus 23 undocked today and met its fiery end. But there you got the Crew Dragon 12 on top, the Soyuz MS 28. Those are the two lifeboats for the 7 astronauts on the space station. And you got 2 cargo ships, all
There was
right?
like 3 or 4 different type vehicles docked, right? At this
Yes,
time.
yes. Down from a couple. Of course, we got rid of the Crew 11 that was docked at the front
Mm-hmm.
on the left, and there was the Grumman was docked there,
Yes.
cargo ship there. But so we love talking about that. Let me go forward again with another image, and 10 humans orbiting the Earth right
And
now.
that's something.
And because you're going to talk about things that humans orbiting the Earth had to do, I wanted to let everyone remember that, hey, this is always serious business, right? Humans orbiting the Earth. It seems easy, but it's really hard, and that's why we've only had 644 since 1961.
You want to do everything you can to make sure they get home okay.
And we've got 7 on the International Space Station. You can't forget the 3 Tachionauts on the
Mm-hmm.
Tiangong Space Station. There are that's kind of a photograph taken from the ground with AI uh, generated pieces and parts on that. But that's a pretty good look at the size of each. Of course, Mikey, we celebrate the shuttles of the month every
Hmm.
month, and March has got one that I know you worked on 67 there.
Yep. Astro.
Ast-
Astro 2.
Astro 2.
Yeah.
Uh,
31 years ago, right? No. What was it? 95, right?
95.
95. Yep.
Yep.
31.
And 31 years ago. How does time fly, right? Any of
Wow.
those other missions strike your fancy, like the Atlas mission?
Yeah.
Had stuff in the payload bay, I know.
That was again this one on the level 4 gang worked on. STS-29D. We did work mid decks for that one. So yeah, there's 3 of them on there. That was kind of part of.
Good, good.
Yep.
Um, we just want to talk briefly about something that you were deeply involved with, the astronomy missions, where uh, twice we sent up some really cool telescopes that
Hmm.
were managed by universities. And you knew Sam Durant's for a while.
Yes.
He passed away. And Paris and Lounge, also of this group, have also passed on. Guy Gardner, haven't seen Guy in a while, Marty. He's always out to Space Center. And Vance Brand was the commander of this mission. And then they flew it again.
Astro 2. Yep. Which is the
And
one that was.
John Grunsfeld was on that. He was at Shuttlefest last year. And you think about John Moore as a spacewalker, but he's a true astronomer.
Yes. Hmm.
What can you say about these missions? As we wanted to say, um, there was going to be this Astro one was I'm going to change the gain on here a little bit. Where's the gain? There we are. Moving the gain up, Marty. Moved
Is
it
that
about
better?
a half a dial.
Okay.
All right, good. This never flew 61E.
That was what we called Astro Zero or Astro Haley at the time. Yep, it was the one that's going to be launched after Challenger, 86, and it would actually had another instrument on it to observe Haley's comet.
Man,
But of course
that'd have
never
been
flew.
cool.
What we call it kind of Astro Haley.
There are the 3 telescopes in the payload bay, as you saw them working on them. They're there in space.
Yep.
Wisconsin's involved in this. Who are the other?
Goddard Space Flight Center, of course, Marshall, Kennedy, a number of different universities, and yeah, that's that telescope package you see there. That's what's on display as part of the restoration project that we're working on at the U.S. Space and Rocket Center in Huntsville, Alabama, right now. And there's a good shot of the display. When you go in the atrium, you make a left-hand turn. This is what you would see. We got basically the whole corner there of the atrium. Right now, we've got the optical sensor package, which you see there. It's like 3 baffles on it. And then the Whoopi experiments, which is Wisconsin ultraviolet.
Whoopi experiments.
Yeah. Let me see if I get this.
Better
Wisconsin
explain that.
ultraviolet photopolarimeter experiment
Okay.
from the
there you
University of
go. Whoopi.
Wisconsin. And so those are 2 on there. We're still trying to get the HUT, which is a Hopkins ultraviolet telescope, and then the UIT, other 2 instruments to put on there later.
Now, these just weren't laying on someone's shelf out at JPL or Kennedy Space Center. You found some of this stuff in junkyards, correct?
Yeah, the cruciform itself, which is the main structure, all it's bolted to, is found in a junkyard and recovered. And the optical sensor package was another piece that was just kind of laying in the weeds. And there's a special bracket that connects that optical sensor package to the main structure. That was another piece that was just laying in the weeds. And one of our team members, weeds, basically literally in the weeds.
Around Kennedy Space Center?
No, it was up in near Marshall. Outside Marshall Space Flight Center, and he just happened to be walking through there and stumbled on this bracket that's basically the only one of it on the planet like it. And we could probably not have put the OSP on if he didn't find that bracket. And the guy didn't know what he had. And the person, Byron Bonds, who's a member of our team, probably one of maybe half a dozen people, literally on the whole planet, to see what was this red bracket. What is this thing sitting in the grass? He recognized it, and he was one of the few people on the planet. So we got that and retrieved that too as well. Yep.
So those of you fans of space museums, U.S. Space and Rocket Center in Huntsville, Alabama, has got to be on your bucket list. I used to go there almost twice a year when I was in Tennessee. Go down to Chattanooga to astronomy event there, and then it's just about an hour and a half from Chattanooga west, and yeah, great facility.
Yep.
It's in my top 5 of all the American space museums. So. Anyway, I wanted to just give you some love for that because I knew it was a lot of hard work with you. And
continuing on, it's still there. It'll be there for a while. So,
but they gave you a lot of nice space. It looks good, and good luck with that. Continued good luck with that.
Thank you, sir.
Here's Mikey's book. It's available on Amazon, published with David Shaler. We talked to David Shaler, gosh, maybe 4 years ago on a link up to England there. Remember that, Marty? That British chap. Marty and I are coming up in 2 weeks on our 6th anniversary.
God, congratulations.
Okay. Yeah.
That is awesome. I don't know how you guys keep doing it.
So I
It's
have
amazing.
to look up, is it tin or aluminum? That's the 6th anniversary gift as you go with the
Oh, I don't know.
things
That's a good
in there.
question.
Yeah. No, but no, it is quite amazing. It's been a labor of love for both of us. If neither one of us enjoyed talking to all of you out there, believe me, we wouldn't do it anymore.
In fact,
So,
David Slayer is actually writing a second book specifically focused on the Astro and Astro Restoration Project.
oh, is
So
he?
that's in the work right now. Yep.
Okay.
So
Well,
anybody
let's
that
get
maybe,
David back
yeah.
on. He does a lot of space history books for Springer, as you see there.
Best, yeah.
He takes on the Gemini program, I know, and some other things. Let me get my my smartphone up here so I can talk to some of y'all. So there's Mikey's book. You've done many stories based on the stories in this book, and you know what? I enjoy reading this book. It's one of the book I can pick up and just open it up where it flips out, start at the chapter or in there and just be entertained. Really,
Thank you, Mark.
really.
Appreciate that.
I'm not a good book reader from front to finish. Marty would probably never read a book without going from the first page to the last page. Am I right, my friend?
You're right.
Yeah, but I open up books and just happen to plop open and start reading it, and I go, I'm meant to read that today."
Yeah.
So that's why the world is full of different people that make it go round and round and round. So let's see who's chimed in today on today's show here. We've got, there we go, hit the live button, and we're going to talk about,
Okay.
let me say hello, Jim McDade. He said he remembers finding a Saturn crew swing arm in White Room in the woods around Marshall. It takes money to restore such abandoned items, and NASA was never given enough to save these artifacts. Good point, Jim.
Yeah.
That's why they're abandoned like that.
Yeah.
And Dave Stangy's watching. He's read a number of David's books, he said.
Okay.
Alan Schmidt's watching. Hey, Alan. Good to see you today. Alan's is offering some help, and he's a great model builder. As we've got Chris Calley says hello
Hi,
to
Chris.
us all. Chris,
Mhm.
6 years and thought it would never last, is what Dave Stangy said. Volume's better now. Thank you all for chiming in there. Ophelia, she is in Toulouse, France.
Welcome.
And yes, and
It'll make the middle of the night there.
by the way, Jim
Sweet.
McDade's out there at
Evening.
Huntsville. He lives in Huntsville there. Did you meet Jim when he was in town? Mark Thel, Doug Forrest. Thank you, Doug, for that email. I'll jump on that when we're done here. So here's what we're going to talk about. There's your first slide. Take it away, Mikey Haddad.
Okay, I want to give you kind of a background. What this is the pressurized elements for station, the way they're mechanically were connected was this mechanism is called a common berthing mechanism, CBM. Had two halves. The active half you see here on the right, it basically had 16 bolts, 4 banks of 4 each, and then actually each of those banks would then control each of the bolts. And then you had the passive side, which is on the attaching element, which just had basically the nuts, alignment guides, and nuts. Again, very, very passive element. But I wanted to show these two pieces because this is basically how the pressurized elements were structurally put together for the station. And again, the next picture actually gives you a photograph of that interface. There you see the controllers, the silver ones, with the active bolts, and then we're bringing a pressurized mating adapter and the passive half. Now look at that, you'll see, well, there's actually 5 boxes per bank. I thought you said there's only 4 bolts per bank. What it is, you have 1 master controller and 4 slave controllers.
That's what you're talking about, these boxes here.
Those silver boxes there.
Yeah, silver boxes, 5 of them.
Had
4 pairs.
Yep, had 1 control each of those bolts. Okay, so that was basically structurally how the pressurized elements were going together. Then once you got them together, there's a space there, what's called a vestibule. And that's where they would run cables and wires and fluid lines and pressure and different commodities. That's how you would physically connect the 2 modules together.
Any module.
Any module together.
All the modules, this is the pattern that they're going
That's
for.
a pattern for all the pressurized elements. Yeah,
So
how
Japan would have to have
something
one
like
side
this.
of this.
Mm-hmm.
Russia,
The airlock,
the ESA,
the
Columbus
lab,
modules.
all those things would be basically the common berthing mechanism.
How'd they come up with that? But
It was,
meetings after meetings
yeah,
after meetings.
lots
I'm
of meetings.
sure.
How would you be able to put something together fairly easily, but make sure that it wasn't going to come apart on you? And so, yeah, 16 bolts hold all that together. Now, one thing I want to bring back up kind of as a background too was this time I was working with under Tip Tallone's group, which is Space Station Hardware Integration Office. For Space Station, they had different subsystems, power, thermal, all that. Well, they considered, there's another one called EV and CS. What is that? Well, it was EVA and Crew Systems they considered as a subsystem space station. Well, that's what I was kind of responsible with under Tip's group, was the lead for that. One of the meetings we were in with the crew one day was they thought, well, okay, structurally we understand this is pretty straightforward. We know it's structurally it's going to go together. We're really concerned about the cables and fluid lines and all those other things that connect between these two after the structural mate. We're really concerned that's not going to fit. It's not going to be too long. It's going to be too short. There's going to be interferences. We want you guys to figure out how to relieve our concern. And so basically I came up with a concept that was called on-orbit constraints test. And that's what we're going to talk about today. How do you do this? Because some of these elements were launched years apart, never saw each other on the ground. How are you going to make sure commodities that run between the two are actually going to work with something that's launched in 98 and something else that's launched in 2001? And that's what this concept was that came up of how we're going to solve that problem. We'll be able to make these things, make sure that they work once they see each other after years apart on orbit. After years apart on the ground, then once they see each other in orbit. So the next slide, basically, this shows the concept. And what it was off to the right is, we'll start out with the flight node. Okay, you got the flight node one that's on the ground. There's cables that run between that and the laboratory module that's launched sometime in the future. So what we do is we take the actual flight node, we take all those flight cables, and again, you can see there's ones on the outside EVA as well as ones on the inside IVA. And we actually connect them up to the node. Are these things going to fit? Do they fit? Do the connections work? Are there interferences? Whatever that is. And then once that is done, okay, we know that fleet interface is good. All those elements going to all those cables and stuff going to node 1 are good. Then we can do the bottom of the chart, which is where we create high fidelity simulators now of the node. Why do we do that? So when the lab comes in, say 2 years later, okay, we use those simulators to make the lab think the actual flight node's still there on the ground, even though it's now been in space for 2 years or whatever. So that's what the bottom shows. And so what we had to do then, we had to create these high fidelity simulators of the element. So when the future element came in, they would match up. We'd be able to run these cables and say, yeah, things fit, things don't fit, there's interferences. So that's the concept of this on-orbit constraints test. Just give you an idea. So then
Very interesting.
yeah, but they liked it. The astronauts say, yeah, you think this is going to work. Okay.
Now we just note here that some of you may have noted constellation systems on the left-hand side in the constellation logo. And boy, there's some people don't even know what constellation was.
Yeah, that's a good point, Mark.
Explain that.
This is actually
2010.
Yeah,
is your paperwork here.
Yeah, this is actually a charts from a 2010 presentation I did at Marshall Space Flight Center, a conference there that they actually presented a paper, and then they had me do this pitch. And so this was how we would work on constellation. This is taking things that we learned during space station and apply them to constellation. Of course, constellation at the time was lunar.
Yeah.
So we think of space station in space. This is kind of you do the same kind of thing. Yes. You kind of do the same thing, except now you do this on the surface of the moon.
Gotcha.
And so this is a presentation to talk about what we did in a space station to make it successful to apply to constellation. And you'll see a lot of these charts all reference the constellation program.
But you would want to use the same type of docking mechanism or lock mechanism on the moon to put other units together. Maybe.
Well, or however the system works, you'd use this concept to do the same approach. Now, the CBM may not be the same. They may be other ways of doing it. But the idea is, how do you make these things work together? So what you see here is actually a graphic representation. What we did is on the right there is that's what's called a test A. That's our high fidelity simulator of the node. Okay, and at this one, in this particular one, you show it going up against the flight airlock. So here we've got emulating the port for the node 1 going up against the airlock. And that's kind of the concept. And so now then you run the cables across. Does it fit? Do things interfere? Whatever. So that's kind of the graphic of it. So you can go to the next chart. This is actually the test aid itself. This is actually a representation of the node 1 interface that went to the airlock. And you'll see up at the top there's electrical connectors on the top and bottom. There's fluid connections on the side. and as the chart shows there, the blue foam is for any hard structure for the CBM components.
I think we understand electrical things going through there, but how about fluid things? What kind of fluids?
You had water, gases that would go between the elements for
Okay.
cooling and other subsystems, other supports. You had eclipse, you had air that would go between those. You have the
Okay.
big ducts for that. And the reason we had the blue foam is if there's interference, we didn't want to damage the flight hardware during these tests. Okay.
Gotcha.
Well, if there's interference with the CBM components, we want them to push up against blue foam, not aluminum structure. So that we figured those are the spots where there's going to be
you would
interference.
damage it if it didn't fit right.
You would damage it if it
you'd
didn't
rather
fit right.
Damage the blue foam.
Well, damage the blue foam. So that was
Yeah.
the idea behind this. So that's one of the test aids, the Node 1 test aid that we use for that. Okay, here's an example of us during that actual test. The Node 1 simulator test aid is off to the right, and then the airlock's off to the left. And you look here and you see down at where the circle is, and one thing too, you're wondering why are these lines crisscrossed, right? You would think it would go straight. These are basically fluid lines. The interface control document was actually, people interpreted it different ways. So now instead of it going directly across, they had to crisscross the lines because of the misinterpretation of the control documents. Well, to do that, it says, okay, well, these lines got to crisscross each other. You look down at the bottom, it didn't reach. During our test,
yeah, too short.
This line would have not reached. If they have we've not done this test, and they went on orbit, they would have gone, the line's too short. What do we do now? You know, what do we do?
Called AutoZone. It looks like a radiator hose there.
And see, this is critical because this is required to power up those elements.
Wow.
And if this isn't, so this is actually during the test on the ground. You see again the astronaut's hand there on the bottom, showing that hey, this doesn't fit. So this is just one of the
Why is
problems
an
we
astronaut
found.
doing that?
Well,
Because he was going to.
Because they were going to do it in space. This is what they do in space. They would make these connections in space after the CBM, docks to it. The two pieces come together.
These are internal, not spacewalk.
Right.
This is inside.
These are the internal ones. We're going to talk about the external ones here in a little bit.
Mm-hmm.
Okay, so the next picture was, well, for fluid lines, okay, this is really one of the coolest tools I've ever seen.
Right, you're totally
The fluid fittings on there was called a gamma fitting. It's basically two flanges come together to make a nice, good seal. And once you do that, it's almost like a welded connection. The problem is putting those two pieces together, okay? When you go to do this, a lot of times what to do is when you put a fluid connection together, right, you have the other piece and you want to back it up with a wrench. So when you tighten this one, the other one doesn't spin. Okay, so you want to back that. Well, there's no way of getting a wrench in there to where the feed through comes through the same time you're putting this fluid line on. So the Marshall guys came up with this ingenious, unbelievable device called a gamma fitting tool.
Right there's the silver part is like a horseshoe. And over here in the astronaut's hand is the, I can't get my fingers to work on this thing.
That's basically a big flange.
Yeah, right
there you go. There you go.
Flange right there.
Yep.
And that's connected to this tool here, though.
Right. So what the tool did is it backed up the one fitting on the feed through, and it also tightened the nut on the fluid line at the same time. Amazing tool. And so basically, this is the tool the crew's going to use on orbit. Will it work here? And so we found these interferences. The tool, even though it was genius, there's still some tight spots. There's different things we had to do because there was interferences. Again, this is during the testing on the ground. We brought all these elements together and all these fluid lines, electrical lines, ran them across that interface. And this is another one of those spots where we found something that really didn't work. It was really too tight. And so we'd have to move things around or whatever to be able to solve that interference. But this tool is used on all the fluid fittings because there were gamma fittings that were part of that interface. Amazing, really cool. And the reason I want to talk about this is in a follow-on picture. You'll see the crew member actually using this on orbit. Okay, now what this is, yeah, go back. Actually, now go back one more. Okay, now what this is, we're going to focus in on the Node 1 and airlock. You see Node 1 and airlock. We're focusing in that interface between those two.
Okay, right above your hand. Point to
right over.
Yeah. There you go.
Up in there, yeah.
Yep, right there.
So we're focusing, and that's the interface. The CBM was birthed, and then now we have to connect those fluid lines, electrical lines between the airlock and node. Okay,
right there, yeah, beside you.
Yeah, it's up over.
Yeah,
there. Am I going behind? But basically, so we're focusing on that interface right there. Okay, next image. Now here's the inside. This is Katie Coleman actually connecting up, and you can see the fluid lines up by her hand there. She's got the tool in her right hand, and she's got the fluid line in her left hand, aligning it and using that tool to connect it on orbit.
And
So what you see is
flashlight in her mouth.
and a flashlight
just
in her
like
mouth to be able to see, because the airlock's on the right side there. You see the two crew members in the airlock. The node is in the foreground here on the left.
There's 4 other astronauts in the backdrop doing stuff.
And so basically they're getting the air. She's connecting the interface between the node 1 and airlock. And now get those commodities feeding the airlock while the crew in there is doing other things to get the airlock ready for operational use. So again,
did Katie train with you on this, or
she didn't come in. She came in for certain ones, but she did, of course, train on the use of the tool. The crew has had extensive training on this tool because it's not a very easy tool to use, but it worked amazing. And this is just some other problems we found with cable interferences. The fluid line on the right side there, it came straight across, and you could see it interfering with the structure. Okay, so what we had to do is actually had to put a 45-degree bend in, another 45-degree bend in to move it away from that structure.
you're talking it is
The
touching,
top right one
yeah,
there. Yeah, that
it's
one there.
actually touching.
It's touching the structure right there. Yeah.
Yeah.
And again, we found that during the test. And again, the bottom, if you look at the bottom, you see all the cabling. It was, I mean, some of these interfaces were just crammed with cables, fluid lines, ducts. I mean, it was just how complex these interfaces were. And this whole idea of this was to test that. We do not want the crew to find a problem on orbit. We don't find that on the ground. And that's what this did. Just found a series of problems on the ground. We fixed those problems before the elements were launched. So when they got into space, those interfaces worked together.
Well, I'm sure a lot of you shade tree mechanics out there are interested in the tools and looking at things like this. So let's say the hand access problem down there in the bottom. Would there be a manual that they would go to that your team had explained that you've got to move this cable out of the way before you stick in the tool to turn 180 degrees one time? And is that sort of thing?
That's exactly what happened. They would put it in a flight procedure that, okay, this piece actually had to go on before this one. If that one went on first, there was an interference. If you put this one on first, there wasn't an interference. So it's exactly what you said. We'd go into the flight procedure and go down those list of steps to put all the stuff together to make sure it all work together. And that's exactly what we do. Is it found that problem, then we'd integrate that into the flight procedure so the crew would do what we did on the ground to make it work, they would do on orbit. Of course,
just think about that. The astronaut training is always training. Okay. I mean, even in space, they're going to be learning something or something.
Sure.
They might not have done this procedure, but you've got the written words to do it.
Yes, sir.
Right.
And they were part of these tests, so they would see this. This is the flight hardware. This is what they're going to see in space. So
you all got questions for Mikey, please chime in there. I'm enjoying talking to my friend here. He's been on our program many, many times and took a little break to work on the Astro 1 restoration project. And we're glad that you're back. And Mikey's already got to show me his program for Shuttle Fest. You're not going to believe it. I'm not going to spring that. You'll see it on Stay Curious one day.
Yes, sir. Okay, now that was an internal. Now we're going to the external ones. This is a graphic representation of what's called the Z1 truss,
See,
deployable
the guy
truss.
spacewalking right there.
And again, this is computer graphic version of what happened on Z1. It had two interfaces. It had an interface to node 1 and an interface to the lab. Well, this tray, this great thing you see in the middle, it's called the deployable tray. There was cables on one side for the node. Then you deploy the tray once the lab got up there, and those cables then connect to the lab. So now you've got one element going to two different other elements, not just one element, two elements externally, EVA-wise. Okay, so, what do? So we got to create test aids against the Z1. And so if you look at the next one, this is basically a graphic representation. What we did is you got the Z1 flight element there on the left. Then on the right, you see the test aid with a representation of the node 1, little arc there on the bottom, and then the lab simulator is next to it. So these two arcs of the outside of the modules that these elements would connect to, that these cables and that would connect to, we had to emulate. Okay, so you start that, then you take the flight hardware and say, okay, does it reach node 1? Then you deploy the tray, does it reach the lab? And that's kind of what this would show. And so I think the next one is actually kind of is this the one actually? Okay, so this is another graphic representation of the test aid against the Z1 flight element. This is an SSPF. This is how it was configured for the test. Okay. Okay, now this is of course, the picture of the real thing. This is the flight Z1, all that gray stuff you see off to the right, or top left, I'm sorry. And then off to the bottom right, you'll see the two little aluminum arc pieces. The one forward end is the node, which is
these pieces here.
Those pieces right in here.
Yeah.
Right in there. There's two arc pieces right in there. The one that's closest to Z1 is the node 1. And so what we do is, of course, those cables deploy from the bottom of the tray and connect to the Node 1 emulator. Does it all reach? Does everything fit? Are there any interferences? Blah, blah, blah. How do you do that? And so that was a demonstration of that interface. How's all that going to work? And then you deploy the tray. I think the next, let me see what the next one is. The next one is the next one. Okay, what it is, this is actually, yeah, this is for the lab. When you deploy the tray, they had these things called circuit interrupt devices that would have to go between those elements. You look at the graphic here and the pictures, and you can see up at the top, the one SID interferes with the handrail, where they're pointing with the finger. The one next to it interfaces with hard structure. There's, there would have been no way that the crew could have done this on orbit. It wouldn't have fit. And so again,
Gotcha.
we found these problems during the test. Solution is on the bottom right there. Instead of having a 90-degree, you have this little angle piece, which is over. Well, it's over there. The angle piece on the bottom right photograph.
Yeah.
That solved the interference problem. And so that was one solution to that interference
So
problem.
instead of having a straight piece here, you had to have the angle piece there. All right.
And then we did the fit check, which is what you see there. Hey, is the fix going to work? We should say, okay, I'll fix this. And we had to retest the fix to make sure the fix is going to work like we thought it would. And that's a representation of.
I'm coming up with some questions here, as I'm really interested in this, and hope you all are getting some of the real blue collar working going on here, so to speak.
It was fun. It's a lot of fun doing this.
So you got the astronauts' time is precious, particularly when they're this close to a launch. And so you show up here, and this astronaut that's pointing there and saying, hey, this ain't going to fit. What's the patience factor, and how much time did you allot for this? A whole morning session?
This could take several days.
Several days.
Yeah,
okay.
several days. Like probably the Node 1.
So when they're coming over here from training for an EVA at the Neurobuoyancy Lab in Houston, they come over here. You're probably scheduling them for at least a couple days here to work on this.
Yeah, we would have meetings and telecons and that to say, okay, we're going to do it on this date. It's probably going to take 2 to 3 days. Can you go all 3 days? No, I could go the first day. Okay, we'll do this on the first day, even though you can't be there the second day. Oh, they have representatives. There may be the ones that actually fly on that mission, or there may be other astronauts could come down and do the work for them, and then take that information back and relay it to them.
Okay.
So yeah, this would take several days for these tests to occur.
Good.
Yeah.
Marty, you quiet over there. Everything going all right? Yeah. And if you have any questions, interject. I know this is not exactly your expertise there as a launch process services, but does any of it connect with you of what you did in the shuttle era?
Without a doubt, no.
Poor Marty.
Now we know.
Yep,
See, I
that's
gotta
it.
ask him.
Yeah,
Don't
sure.
want him sitting over there just doing nothing.
By the way,
All
the
right.
man behind that does so much work here.
Yeah, we've had a lot of fun, and he brings a lot to it. I don't want to ignore that Marty worked on the shuttle era, and mostly with the computer systems on the engines there. And in fact, the little box on the SSME, that's your baby, right?
Oh
The
wow,
little
okay.
control box on the SSME.
Those things
So
are still miracle workers.
We've
Those
learned that
main
from
engines.
Kevin Hostrasser. You know Kevin Hostrasser
What's
engine?
that? Mm.
Kevin's had some very popular shows talking about engines, and he made the 3D printed engines of the
Oh.
F1 and SSME we have.
Oh, okay.
That I'll show you
Sweet.
before you leave. Hope you're enjoying this. If you got a question of Mikey about anything about working in the payload bay, let me know. Well, there's one right there. That's a Virginia number. I'm going to say, talk to you later.
You're a popular man, Mark. Okay, this next one is this actually shows the connections between that Z1 truss and the lab on orbit. This is the what we work towards. Is
Known as the rat's nest.
Let's
Due
go
to
the rat's
fact
nest,
that
'cause
umbilicals are
you can see all the cables
all over
and
the place.
umbilicals all over the place. And so this is basically this is what it looked like after they did the connections and everything was successful on orbit. So our testing, our changes to the hardware because of the interferences we found. So this is the end result: is it all fit together and worked on orbit.
Would you be privy to this as like a follow-up that have a meeting like, hey, they installed all the ammonia lines there and the little anomaly you pointed out, they were happy to know that was going to happen, and so was there a lessons learned follow-up?
Oh yes, yeah, there was definitely. In fact, my one chart it talks about lessons learned. And no, not yet,
Oh,
but
okay.
coming up. But yeah, that was one of the things is then each crew then would take those lessons and apply to the next. So the crews on these missions, just as the early missions on space station. And so they would say, okay, this is what we learned by doing these tests and that. And then they would, of course, relay that to the future astronauts that are flying on other flights where this kind of work would happen with other elements. Yeah, it was a ripple effect, and it really was successful. It was really.
And if they had to go back there and do a maintenance job there, they got these photos to see
Sure. Yep.
of what it was 3 months ago or whatever when the expedition before them did this
Yes, sir.
maintenance on there.
Yep. The photos were huge and
we did a program on Dexter, the little Canadian robot out. Did you ever deal with Dexter much?
I never did. No, unfortunately,
Okay.
it's an amazing piece of equipment, but I never did myself. No, sir.
Yeah, we enjoyed sharing that with our viewers yesterday.
Okay, now this one is a very interesting. This is kind of, it's got a lot there. I know it's probably really confusing, but bottom line, what it is, this is 3 elements that we had to simulate, and there's only one little arm there. You see, it says the S1. What is it? S0 truss flight umbilical. That's the only flight component in this whole configuration. But it went to node 3 of the lab, and S0.
Which is
It's where it says, you see where it says S0 right there. That little bar right there as it goes across, where it says S0 truss to flight node
the
flight
gray
flight
bar
umbilical.
across the middle there.
That's the only flight piece in there. The rest of that is simulation, is test aids. With such a complex interface, we had to simulate all these other things with test aids. Is this umbilical going to reach? And if you look at the bottom right,
and truss is the backbone structure, like you would think of the when you say truss, think of a frame of a house.
It's
2x4s that frame up for the drywall.
Yeah, like on your roof or something.
Yeah, right.
And the way station was
Joists
built,
is for your roof would probably be better.
something like that.
Yeah.
Yeah. What it was is S0 was the S0 truss was the center truss, and the way space station, the way the nomenclature was, is S1, S2, S3 were the starboard trusses that went out from S0.
I don't see a scale there. That's pretty big, isn't it?
Oh, it's huge.
Yeah,
It's
that's huge. It looks like it's not, but that's probably 20 feet long.
Yeah, because then you look at the bottom right there, the bottom photograph, that shows the actual deployment of the umbilical to the flight interface and does it working.
Okay. Marty's got a question for us from our intelligent group staying curious today.
Yeah, mostly Park is asking, so CAD modeling didn't show the interfaces.
CAD modeling helped. Yeah, but this was actually, that's a very, very good question. In fact, I should describe how we made these test aids. The test aids, what we would do is after the flight element, before the flight element would fly, we'd take called digital pre-assembly. It's something they use on the Boeing 777. And we digitally make a digital copy of that interface, of that node 1 element. Then from that digital interface or a digital model, then we'd create the actual test aid. And it was down to 1,000th of an inch. So yeah, the CAD cam that was used was good, but it wasn't the flight element. But we did use CAD cam to basically create the test aids from the flight elements, if that makes sense. So we had the CAD cam was good, but we wanted the flight hardware do it with your hands kind of. So the CAD cam did help out a lot, but to verify for sure, we wanted to make sure that we did the flight-to-flight interface with the real thing. So that's a very good question. Yeah. I forgot to mention about how we created those test aids.
Park
Yeah.
Marion there. Thank you for that.
Yeah. Okay, and this is just another example. This one had bend radius. We had a bend radius problem.
Are you done talking about
Yeah,
that? I think that's like you're looking at this picture here. You're looking at 30 feet from one end to the other there. So.
Very complex test, but again, it was very successful. Yep. And this is just one showing bend radius. This is another thing. Was there interferences? This one shows the cable or the fluid line.
Bend radius problem.
Yeah, what it is you have what's called bend radius, where you don't want to bend a cable or a fluid line more than what the bend radius talks about, because you can cause undue stresses on the end, damage to the hardware.
I never knew there was such a value, Marty, on stuff. But you're bending this a U-turn around the blue structure there,
right,
and on the right there. So it has tolerances, and everything is known.
Basically, what we did is we took the blue foam and said the bend radius. This is the required bend radius using blue foam, and we put it up against the flight hardware to see, hey, does this satisfy the bend radius?
Simulated flight hardware is the blue there.
Yeah,
I dig it. I get it, Marty. Go ahead.
Rock, you never heard of bend radius, but
No.
Bruce talks to you about that over the years a lot. He's talking about hooking up cables to your
Yeah.
computer or to the camera.
Yeah, he does
complains
talk
about the
that,
bend
yeah.
radius.
Yeah, there you go. Yeah. now you're reminding me all these cables and stuff. Our IT guy, Bruce Jacobs,
Okay.
he is an IT guy and a
Okay.
good one. Oh yeah, yeah. There's when you get emails from him, our IT guy, it's usually 2:30 in the morning, and it looks like a manual with indentions and 3A, B, 3C, and stuff like that. We love him. He's a good guy.
The one thing I forgot to mention too on a lot of these cables and fluid lines, there's what's called clocking. So you can have a cable.
I've heard of clocking.
Okay, clocking. What it is
Not sure what it is.
Is the cable, the connector that it's going to. The cable only goes on one way.
Okay.
There's like keys in it, like can call a master key, and the cable can only fit one way. You can't put the thing on all. Now fluid lines are different. The cables, you got to put it on this way. It's the only way it's going to work. You can't turn it 90 degrees. You can't turn it 45 degrees. It's got to go on this way. Well, what we found on some of these tests were the clocking was 90 degrees off. Okay, well, data cables, you can probably turn that enough to get it on. Power cables, which are like that thick, you're never going to turn that thing a degree. So if that clocking is off by a degree, it's not going to fit. And that was another thing we tested was the clocking of these things to make sure the cables not only went in, but they were clocked correctly. And then what happened, a lot of them, with the way that they connect up, is you'd have a bail you'd throw. So yeah, you would connect it up, but when you went to throw the bail, it would interfere with cables next to it, structure, whatever. So we had to test all those kind of things had to be tested. The whole procedure,
the bail is a little tab that connects it.
It's like you see a fire hose where the firemen they push that thing.
Yeah.
It's almost like you have on your garden hose where you push it forward and the fluid starts and you pull it back. That was the same kind of thing, but what it did is it drove the connector or drove the fluid line to basically mate. I wish I had a better picture of that, but it's basically the way they would mate these electrical connectors. You push it in, then you throw the bail, and that would be a hard mate, basically. So that was just other things we found were interference problems that we had to figure out how to fix.
Well, these are the kind of things we talk about on Stay Curious frequently with people that I love calling national treasures, because Mikey Haddad did things that you're hearing today that no other one in America did. Let's face it, no one's got another space station to put together.
This was the only place we did it.
That's why we consider you and Marty national treasures.
Thank you very much.
And it's an important part of our future here at the American Space Museum. It's just doggone fun to talk about, and we have a whole group of people here that are interested in it. So thank you, Mikey, for taking your time to put this together for us.
Yeah, there's just a couple extra. Again, this was back in Constellation days. Again, this is part of the presentation from that presentation I did back in 2010. So this is when we were talking about the configuration of moon base for Constellation program.
Yeah,
and
this
so it's just
not political, but
No.
when the torch passed from young Bush to President Barack Obama, he let the Constellation program go.
Yeah, it was canceled.
But then he had a backup plan. We're going to commercialize Cape Canaveral and Cape Kennedy, and we have. You've seen the transformation.
Sure. Yeah.
But this was the dream.
Well, this is in 2010.
15 years ago.
Yeah, this is in 20. This is trying to apply what we learned for station, apply that to the constellation elements that we're going to go to the moon. That same idea to make sure these things are all going to work. And that's
and no matter what, we go back as Artemis or go back as Winkle. Okay. The Winkle program. I kind of like that. You have to have this same technology that you're sharing with us today.
Yes, sir.
To make sure everything fits, because I just think it's incredible. An entire International Space Station put together, and it was never assembled on Earth and disassembled and then put up there. It was just everybody's CAD drawings and blueprints and
elements made years apart, had them made in orbit. And one thing too, to apply this kind of to the Artemis program, you think of the gateway that's supposed to orbit the moon, if that still, happens, applying this kind of that, because the gateway pieces will be coming up in different flights. So you could apply this kind of process to making sure the gateway elements and then of course the surface elements once you get back to the moon. Yep.
Excellent. And
this is just a graphical representation doing the same thing. You take the surface hab, you find the elements, you connect it up to that. Surface hab would launch. You keep those elements, and the second surface hab would be underground. You do the same process as we did. Create a test state of hab 1, so when you made it to hab 2, you can test those interfaces, see if they work. That's kind of what this was. Okay, and then what I tried to present this as, to kill two birds with one stone. When you connect this stuff up, you're basically connecting the flight elements, the flight cables. I thought, well, if you can piggyback this on a test, you're going to use the flight cables, like say here. the test tab too. You're going to use those flight interface cables to make sure the flight cables work. Then you're going to connect up a simulator, the test, combine those two, run the test cell, test configuration, the test cables to simulated test aid, then the flight cables. So you get a test of the cables themselves as well as the test aid they physically fit. So you get a functional as well as a physical verification. That's what that idea was. Just piggyback it on the test.
Not to get you in trouble, but to ask you a question about today's private companies. Are they doing these type of tests, or are they eliminating some of them to save money?
Well, good question. I've been contacted about this process possibly being used for certain aspects of Artemis.
Okay.
Again, it's up to private companies to figure out whether this would be a process they can use or not. Would be helpful for them. And again, there may be a whole nother means. There may not be these cables and fluid lines. It may be a hard mate and everything connects up automatically. And so you may not even need to do this. So it depends on the design of the hardware. So we just see what the future design is.
Well, it's good to know that new companies are reaching out to legacy people like yourself that been there, done that.
Yes, sir.
Because I think that's part of the lack of cadence is what I want to say. And always being politically correct here on our program. In fact, here's all the
and this is a
there's
lesson.
all the Marquette disclaimers here of whatever I say is not all right. Marty's down there. I did not say that. If Mark says I said it on there, no, this is your slide.
This is basically this is just lessons. There's a lot of words here. Basically, there's a lot of things we learned, and this is so to apply it towards. Again, this is for part of the presentation that was done. The main thing is to get those elements, those cables that go between the elements made early. Everybody say for the lab. Okay, well, these cables that go between node 1 and the lab, we don't need them for 3 years because the lab doesn't fly for 3 years. So we don't need to create those cables for 3 years. Like, nope. You need to create them when the first element goes so you can get to the first element. So those cables got to be ready 3 years before the flight element. And so that's just basically one of the main lessons learned is you got to have that hardware available before the first element flies, not when the second one, when you're actually going to put it together in space. And it's just other lessons learned there that we can talk about.
Early purchase of flight connectors, design and build of flight jumpers, flight crew involved to get familiar with flight hardware and on-orbit surface operations, flight procedures verified or generated, fabricate and assembly test aids in Florida to allow quick turnaround and repair of test aids. And this not only creates efficiency in our space program, but sometimes saves money.
Oh, yes, a lot.
And
yes,
therefore, you get recognized for that.
Yes, sir.
Coming up here.
And that's kind of what I got my Silver Snoopy Award for, was for this process, this on-orbit constraints test concept that we came up with and we used. Yeah, I got a Silver Snoopy Award for that.
And we have, I want to show the Silver Snoopy is actually a Silver Snoopy.
Yeah.
About only an inch tall. It's a very small little guy.
You get a pin as well as the award, yes.
And appreciation there. And your award was presented by, I know you talked about this lady quite a bit, and she passed away of cancer, but she had 5 flights, Janice Voss.
JV, a very good friend of mine.
Yeah.
Very, very good friend
What can you say about JV's, what everybody called her?
She called her JV, yeah.
Yeah.
That was what we knew her by. Yeah.
She's sweet.
She was.
Lady, but I mean, you say sweet lady, hell, she went to space 5 times. Nothing sweet about that.
I'll tell you, and she
going
was
to that rocket launch.
She was smart
and re-entry and
very physical able and very sharp, very smart. But you could just talk with you like your
no relation to James Voss.
No, and they weren't married. Everybody says, "Oh, they were married." No, they were never married.
There's an astronaut named James Voss, also very experienced, as well as Jerry Ross. But they were kin in any way. Did they ever look into that?
I don't think so.
I don't think so. Or they didn't look into it, or they weren't.
I don't think they looked into it.
Okay.
I'm not sure.
All right. Well, this is.
And then the last,
I can see in his little twinkle in his eye there, he misses Janice. And
yeah, she was.
This is why we have a beautiful group of people that support our museum, because they dealt with the humans that orbited the Earth, and they're not on a pedestal. They're just regular people, right?
Yes.
Let people know that, right?
She was. Yeah, you could talk to her like your next door neighbor. She loved chocolate. My gosh, her and my cousin Lisa, they became best friends with chocolate. In fact, she was able to actually get some of the chocolate that Janice liked. Janice was able to fly on the mission, and she was able to make that
probably
happen.
knew a few Belgians that make good chocolate there. So
and there's just one more picture.
Yep, we got one more slide there.
This was actually when I did the paper and the presentation for the conference. They actually selected my paper as one of the top papers of the conference.
Oh,
which
good.
was just I just couldn't believe it. I said, "What?" She goes, "Yeah, yours is one of the top papers for the conference," and it was made into this book. They took the top papers from the conference, and this is the book that those papers were in, and mine's in there. So I just wanted to kind of show that. It was very, 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 very fortunate that I got picked as that. So that was it. That's the last one for me.
Well, we enjoyed talking to Mikey Haddad here. Here's the space station we talked about. What thought did I have there about you? I was looking at this picture thinking of, what an amazing guy you are. Mikey also worked very close with Sally Ride
Mm-hmm.
on a book that cover reminded me of it, about the future of NASA, correct?
Yeah, at the time it was
So-
called the Leadership in Space. It was
Leadership in
Sally
Space.
Ride Report.
And you worked with her on that as
Yes,
her
sir.
right hand. You were the chosen person at Kennedy Space Center to go with her and tell them what we need at KSC,
Yes,
correct?
sir. Yes, sir. They would pick one person from each of the space centers, and I was fortunate enough to get picked as the KSC person. One person from all the Kennedy
And
Space
Mikey
Center.
talked about that when you did an excellent program on your career there, and I always love that about you, buddy. So Marty's
you.
got a
Thank you.
question.
Yes, sir.
Yeah, before I have two questions now, but before I ask the question, everything Mikey's talking about can boil down to one thing, attention to detail.
Yeah.
And that goes throughout the whole space program, not just the work Mikey did, but that's from unmanned through what SpaceX is doing.
Sure. Oh, yeah.
And
Yeah,
when you
attention
take
to
your
detail.
eye off to the detail, you end up with a problem,
It'll burn
Or
you every
two,
time.
like
You-
we've
you-
seen recently
It'll burn you
play
every time.
out.
And again, we have two questions. We have one from Mostly Park. Did they check if the dimensions didn't change on the old airlock after 2 years in space?
Good question. That's a good question. I know that the CBM, the bolts, I think they would run and retorque to make sure that interface stayed secure. I think there was a maintenance procedure to verify that didn't loosen up and basically didn't the gap, because there was actually seals there that, of course, if those seals started to leak, you would think, okay, maybe that interface came apart. Hopefully they answered that question.
Well, he might also be thinking about, everybody knows the contraction and expansion by the temperatures and so forth. But these hardware is designed within tolerances of that, right?
Oh, yes, sir. Yeah. Be able to take that over decades in space. Yeah.
Go ahead, Marty.
And RG Jubilee has a comment, and Mark, I think you already have this plan. She's saying, Mark, you should do a show on the origins of how Snoopy became popular with the space program. I think you have that in work.
We've got Mr. John Tribe, hypergolic fuel legend of Rockwell, is going to come and talk about the Snoopies
Okay.
that were a little pep up, or sometimes a fun little disparaging comments about managers and so forth. But yeah, we're going to get with great idea there. We need
Yes.
to, I said to Marty the other day, I'm trying to think of just some canned shows that I could research and do that aren't space history, but about the space historical elements of it.
That's a good question. A lot of people ask me why is Snoopy picked out as for the award, and why? Yeah, that'd be a great segment.
Yeah.
Talk about that whole history, how Snoopy
Uh,
became part of all that.
Part of it started with Apollo 10 going to the moon and having to name two spacecraft. One became Charlie Brown, the other Snoopy.
Mhm.
And then when we went on Apollo 11, was going to land on the moon, NASA said, we need to get serious about this, all right, with our call signs. They were call signs.
Yep.
But we'll do that and find out the legend of Snoopy. Also, Gary Hart and Wizard of Id was part of the Skylab program. I always liked that cartoon on there.
Mhm.
You look at cartoons much anymore?
Every once in a while, sure, yeah, still
But
do.
not like we used to.
No, but I still.
After the sports, then the cartoons,
yeah,
then the
it used to be the sports and cartoons.
yeah. I've even seen a box score in several years.
Well, it's all online now.
Yeah,
We
look
don't get
at
the
it's
paper
all
anymore.
online
Yeah.
exactly there. So we've got George Hastings watching. That is Marty's kinfolk, isn't it?
Yeah.
Oh, isn't he? Okay, George. That's the other George.
That's the other George.
Yeah, yeah. He's a heck no. And Hastings is going, don't you hook me up with him. CT Cubing, Tommy Usiak, good that you're
Tom.
watching today.
Okay.
I'll bet there's might be some crocuses in his yard up in Lancaster, Pennsylvania. trying to bring spring up there. Alan Schmidt's watching. Thank you, Alan. Alan, I keep thinking about that Gemini module you teased me with. So I'll be in the building Saturday, so stop on by. Chris Callie, talked to Chris today. He's one of our leaders of Shuttle Fest. Jim McDade, great comments by Jim. I see you on there. Tom Celentano, Dean Babcock, Mark Thel, Mostly Parked, Ophelia Sauterell, Doug Forrest, RG Jubilee, and Dave Stangy. And
welcome all. Thank you.
Yeah, well, thank you all for watching. I know Steve Jokum said that he and his wife are going on a little Thursday, Friday trip there outside of Fox Lake, Illinois, and glad that you all support Steve's modeling business. He does the shuttle thermal protection decals and stuff like that at his Lake County Spaceport up here in Fox Lake, Illinois. So great, good program. I really enjoyed that. You know, this is like Marty says, the attention to detail is unrelenting, because when you're talking about these tests, you've got the person doing the test, you got another person holding the manual that's checking off that the person doing the test is doing it right, and then you've got a quality inspector from NASA over those two shoulders.
A different set of eyes looking at everything. Yep, just to make sure it's double checked.
That's three people. Is there a fourth person involved?
Oh yeah, there's lots of people you didn't see on that, but there's dozens of people that are supporting that and right around that area. Why the crew member is doing those?
That's why I wanted to.
We're doing those tests. Yeah, it's
emphasize.
Probably a lot of people involved, because you got those are the main players with direct hands-on, but you got all the support people in that that are back there supporting, make sure the test aid's all secured, that the thing's not going to fall apart. People feeding the hardware to the person that's doing the installation. So there's a lot of support people that you don't see. They're kind of not in those photographs that know how to make this happen. And of course, you got all the preps. I mean, creating those test aids to the 1,000th of an inch detail was huge. That was the main thing, was to be able to create a very high fidelity representation of that flight interface, so you knew this is exactly kind of what it looked like when you brought the next element in.
Very
critical.
Yep. This, like, we're talking about these elements here that connect these two lab and the node there, all standardized, all part of the International Space Station effort. 25 years, like I like to say, Mikey, if you're 25 years or know somebody 25 years or younger, or older, I mean, they've never breathed a breath on Earth that someone in space hasn't been breathing.
Isn't that something?
Up there.
That's just amazing.
Yeah. So
to think about it that way, my gosh.
So anyway, Marty, thank you for going through a little bit of problems we had this morning. Thank you, Trekkie Techie, for jumping on that. And we're looking forward to Friday. I'm going to queue up some astronomy. I'm also going to look at some Artemis stories that have been floating around. One by the CBS Dean of Astronauts, Bill Harwood. Okay, basically saying what we've been saying for a year. You can't put something on the moon that's taller than it is wider. Okay, it's going to fall over. All right. So we're going to get back to some of that tomorrow and tell you what to look at in your night skies over the weekend. Yes, Marty.
Mark, I thought we were doing that recorded show.
We're going to change on that. My date changed from what I was. Pardon me?
Mine didn't change.
That's okay. Well, I can have Raj in here to do it for me there. We were going to do a recorded show. We're going to do that next Thursday when I go to Orlando to do a couple talks over there. So, yeah, I'll tell you later. My plans changed on Friday, and but that's no big deal. We'll just rack it up again. Marty's going to be out chasing the white ball out there.
Ah, well, no, that doesn't happen. That's no fun, is it?
Yeah.
Somebody has to do it.
That's right. Oh well, you'll do it. Way to go, Marty.
Thank you very much, Mikey.
Thank you for the.
Oh, always. We can't wait for you to come back on next month. Figure out something else we can talk about, or maybe you just want to ask Mikey questions. Let's do that. Get you in here, because there's a lot of people that love just asking Terry White questions, and we seem to burn up an hour every time we do that. So, thank you so much. From one Buckeye to another, we thank you for watching today. Until tomorrow, Might take you out the backyard to see what you can see in our wonderful universe. I'm Mark Marquez saying, come on back and bridge the space between us. Thank you, Mikey.
You're welcome. Thank you.